Welcome to our lecture on the Weierstrass Approximation Theorem. Today, we are going to explore one of the most beautiful and powerful results in mathematical analysis, showing how the simplest mathematical building blocks can construct infinite complexity. Before we dive into the rigorous math, let us build some intuition. Imagine you are a sculptor trying to carve a beautifully complex, wavy statue out of wood, but you only have a set of standard, simple chisels. In this analogy, a continuous function is like that unbroken, smooth surface of the statue. A polynomial, which only uses basic addition and multiplication, is like the simple cut made by your chisel. The Weierstrass Approximation Theorem is a magical guarantee for the mathematical sculptor. It tells us that no matter how complicated your unbroken statue is, you can combine your simple chisel cuts to match the statue's shape as closely as you could possibly want. Now that we have the intuition, let us state this foundational concept formally. Let f be a continuous real-valued function defined on a closed interval from a to b. The theorem states that for every epsilon greater than 0, there exists a polynomial p of x such that the absolute difference between f of x and p of x is strictly less than epsilon for all x in that interval. Here, the Greek letter epsilon represents a tiny user-defined error margin. Because this holds for all x simultaneously, we call it a uniform approximation. The maximum vertical gap between the true curve and the polynomial never exceeds epsilon, anywhere on the graph. The original theorem tells us that a polynomial exists, but it does not tell us how to find it. The most famous and constructive proof of this theorem was given by the mathematician Sergei Bernstein in 1912. He did not just say the polynomial exists, he provided a mathematical recipe to actually build it. He introduced what we now call Bernstein polynomials. His brilliant idea was to take exact samples of the target function at evenly spaced points and then blend them together using smooth, bump-shaped polynomial weights. As we take more samples, the blend gets closer and closer to the true function. Let us look at the exact formula Bernstein created. For a function defined on the interval 0 to 1, the nth Bernstein polynomial is defined by this structured sum. Conceptually, it is a weighted average. The term f of k over n is simply the exact value of our target function at specific evenly spaced sample points. The rest of the expression, involving the binomial coefficient, creates a smooth bump-shaped curve that peaks exactly at that sample point. By adding these up from k equals 0 to n, we are blending these weighted samples together. As n increases, we use more samples, and the approximation becomes incredibly accurate. To prove that this blending process actually works, we need to establish some basic properties of these polynomial weights. First, we want to know what happens when we add all the weights together. We can figure this out by looking at the standard binomial theorem. If we expand the expression x plus 1 minus x raised to the power of n, we get exactly the sum of our polynomial weights. But notice that inside the parentheses, x and minus x cancel out, leaving just 1. And 1 raised to any power is still 1. This means that at any specific point x, all our polynomial weights add up to exactly 1, or 100%. Because the weights sum to 1, our approximation stays perfectly grounded to the scale of the original function. Now we need a second property related to how spread out these weights are. Think of this like variance in statistics. We want to know how much influence the sample points far away from our current position have on the final sum. By calculating the weighted average of the squared physical distances between our current position x and the sample point k by n, mathematicians found it equals x times 1 minus x all divided by n. This variance property is the key to controlling the error. Now we look at the actual error between our target function and our polynomial approximation. We want to prove this error is smaller than our chosen tolerance epsilon. Because we already proved that the weights add up to exactly 1, we can mathematically bring f of x inside the summation. Taking the absolute value gives us the total worst-case error. To prove this sum can be made incredibly small, we split the sum into two separate groups. Group 1 contains the terms where the sample point is physically very close to x. Group 2 contains the terms where the sample point is far away from x. Here is where it all comes together. Because our function is continuous on a closed interval, it is uniformly continuous. This guarantees that for the close points in group 1, the difference in function values is tiny, less than epsilon over 2. For the far points in group 2, we use the variance property we just found. As n gets very large, the denominator grows, and the contribution of these far points shrinks to 0. By choosing a large enough n, the combined error from both groups becomes strictly less than epsilon. This gives our final result, proving that the Bernstein polynomial perfectly approximates the function. We have proven the theorem using Bernstein polynomials, but in practice, if a function is very smooth and well-behaved, there are faster ways to find an approximation. For infinitely smooth functions, the Taylor polynomial is a highly practical tool. The Weierstrass theorem guarantees a polynomial exists, and the Taylor series gives us a direct way to construct it. To ensure our approximation meets a specific tolerance, we use the Lagrange error bound to determine exactly how many terms we need to keep. Let us see this in action by approximating the exponential curve on the interval 0 to 1, keeping the error strictly below 0.1. To find out how many terms of the Taylor series we need, we use the Lagrange error bound formula. Conceptually, this formula tells us the maximum possible mistake our Taylor polynomial can make. Let us break down the symbols. The capital M represents the maximum possible value of the next derivative of our function on the given interval. The exclamation mark is a factorial, meaning we multiply the number by all positive whole numbers smaller than it. Finally, x is our position on the interval. If we increase the degree n, the factorial in the denominator grows extremely fast, which drives the overall error down towards 0. Let us work through the example. We are given the function e to the power of x on the interval 0 to 1, and we need the error to be less than 0.1. First, we need to find m. The derivative of e to the x is always just e to the x. On our interval, its maximum value occurs at x equals 1, which is about 2.718. To be safe and make the math easier, we overestimate this and set m equals 3. The maximum value of x on our interval is simply 1. Plugging these values into our error formula simplifies the expression significantly, leaving us with 3 divided by n plus 1 factorial. Now we just need to find a whole number n that makes this fraction smaller than our target tolerance of 0.1. We do this by testing small integer values. If we choose n equals 3, the denominator becomes 4 factorial, which is 24. 3 over 24 is 0.125, which is slightly too big. So we test n equals 4. The denominator becomes 5 factorial, or 120. 3 over 120 is 0.025, which is well below our required threshold. Therefore, a fourth-degree Taylor polynomial successfully approximates the exponential curve within the desired error margin. Approximating a smooth curve like an exponential is great, but the true unmatched power of the Weierstrass Approximation Theorem is that it works even for functions that are not smooth at all. Consider the absolute value function on the interval -1 to 1. This function has a sharp V-shaped corner exactly at x equals 0. Because of this sharp corner, the function has no derivative at 0. This means we cannot use a Taylor series at all because the required derivatives simply do not exist. Instead, we must use an iterative sequence of polynomials that slowly morphs into the absolute value shape. To build this approximation, mathematicians developed a clever iterative recipe. We define our starting polynomial, p0 of x, as just the number 0, which is a flat horizontal line. Then we use this formula to find the next polynomial in the sequence. We take the current polynomial, Pn of x, and add a correction term. This correction term is based on the difference between x squared and the square of our current polynomial. Conceptually, this formula looks at where the current approximation is failing and adds just the right amount of curvature to push it closer to the true V shape of the absolute value function. Let us calculate the first few steps to see how the shape begins to change. We are given our starting point, P0 equals 0. To find P1, we plug P0 into our iterative recipe. Substituting 0 into the equation makes the math very simple. We get 0 plus 1/2 times the quantity x squared minus 0 squared. This simplifies directly to 1/2 x squared. Our first real approximation is a wide U-shaped parabola. It is completely smooth at the bottom, not sharp, but it is starting to curve upward on both sides, mimicking the general trend of the absolute value function. To get an even better fit, we repeat the process. We take our new polynomial, P1, and plug it back into the recipe to get P2. We substitute 1/2 x squared everywhere we see Pn in the formula. When we expand the squared term inside the parentheses and distribute the 1/2, we get a new polynomial of degree 4, x squared minus 1/8 x to the 4th. This new polynomial hugs the V shape much closer than the previous one. If we kept repeating this process, the polynomials would get higher and higher in degree, pressing tighter and tighter into that sharp corner. Let us look at exactly what this iterative process achieves visually. On this graph, the solid blue line is our target, the absolute value function, with its sharp corner at the origin. The red dashed line is our degree 2 approximation, a simple wide parabola. The green dashed line is the degree 4 polynomial we just calculated, which is already pulling much closer to the straight sides. Finally, the orange dashed line shows a degree 10 approximation. You can see how the smooth curves are being forced to bend sharper and sharper at the origin. The diagram beautifully illustrates that even jagged continuous functions can be approximated by smooth polynomials. So, why does this theorem matter so much outside of pure mathematics? In the real world, computers and microchips are fundamentally simple machines. At the hardware level, they only know how to perform basic arithmetic like addition and multiplication. This means a computer can only naturally calculate polynomials. When you ask a calculator to find the sine of an angle, it cannot compute the true abstract mathematical function. Instead, engineers rely entirely on the Weierstrass Approximation Theorem to find a polynomial that perfectly mimics the sine wave up to the 15 decimal places on your screen. Without this theorem, modern digital computing would be completely impossible. Let us summarize what we have learned today. The Weierstrass Approximation Theorem is a foundational bridge between abstract continuous functions and computable polynomials. It guarantees that any unbroken curve, no matter how complex, can be uniformly approximated by a smooth polynomial to any desired accuracy. We saw how Bernstein polynomials provide a mathematical recipe to actually build these approximations. We also proved that this works for perfectly smooth curves like exponentials and even jagged shapes with sharp corners. You have now mastered a powerful concept that proves simple building blocks can construct infinite complexity. Great job!